So we're doing longest increasing subsequence. This is a fairly classic dynamic programming problem, and if you don't know dynamic programming, it's probably impossible to solve in a valid time complexity, like in an efficient time complexity. Yeah, and it's pretty simple when you understand it. So here you're given an array of numbers, okay, and you want to find the strictly increasing subsequence in it, the longest strictly increasing subsequence. So for this, you look at 10, 9, 2. This is the if we just look at this, the longest increasing subsequence is just 1, since it's decreasing all the way through. But if you look at it all, you can notice that 2, 3, 7, 101 or 18, like one of those, will make 4, and that means these numbers are the longest increasing subsequence within this array. If you look at another example here, you can see that 0, 1, 2, and 3 are also the longest increasing subsequence within this whole subarray, within this whole array. So how do you solve this using dynamic programming? Well, if we look at the solution by hype it, the fairly classic way of solving it iteratively is creating a DP array, and then this is an O of n squared solution, which is not very efficient, but it does work, as you can see here. And you iterate through the array twice. You go through the first one, basically pick a number. The second one, you go from 0 to that number, and then you check the array. Hey, is this number that we're on, nums j, is it less than nums I? So let's say we're on 2, for example. You can check if it's less than. It's not, so this whole loop won't do anything. It'll just be 1. Let me check it here. So nums I, yeah, greater than nums j. And dpi is less than dpj plus 1. Yeah. Okay, so it's gonna be ones, since our whole array is just made of ones. So now let's say we're jumping to 3 here. So now nums I is 3. And then once it gets the second for loop to 2, here this will pass, and this will be incremented by 1. So this keeps on going till you reach the end and you get 4. And then here we basically do another for loop and check the biggest number within the DP array. In this case, the biggest number is 4, which is then returned, and that's your answer. So that's O of n squared, but there are better ways to do it. For example, here by Diet Pepsi, there's an O of n log n way of doing it. Instead of going through the whole array twice, we can go through the whole array once and then do a binary search as the second loop. So here we replace the inner for loop with a while loop that does binary search, and the way we do it is a bit different. So instead of just going through the DP array and then looking for the longest increasing subsequence from the DP array is going to store the longest increasing subsequence that we can find using binary search. So as you can see here, we initialize a variable called s, and then we start it at 0, and then we say, hey, let I start at 0 and j equal to s. So this for loop at the first time, this while loop is not going to be included at the first time. And here we're going to increase s, and then we say, hey, find the middle value between I and j. And if it is less than x, which is the current number that we have, so in this case it's 9, I believe. So since s is 1, it's 0. Oh, so it's 10. If it is less than x, then you append it. If it isn't, then you just make dpi, which in this case is 0, equal to x, which in this case is 9. So you basically build up the longest increasing subsequence. So here, if you go again from 2, what's going to happen is that the DPI is still going to be 0 at the end of it, and it'll be equal to 2. And then you keep on going with s only being equal to 1 until you get to 3. In this case, you're going to append I here is going to be equal to 1, and then the DP array is going to be equal to 2 and 3. And since we're only interested in the s, in the size of it, we return s at the end. But this is a very versatile solution, since you can also return the subarray itself. So we can try it right here. For example, let's go for loop in num in dp, and then we see out num and l. I believe it's going to print out 2, 3, 7, and 18. 2, 3, 7, 18, and the rest are ones, because we initialize the array with the size of the original array, but we're only interested in the size. So there you go. That's a pretty versatile solution that you can use not only for this problem, but also for other similar problems. Now, I'm gonna move on to a more C++ specific solution proposed by DTCCWL. And here you do the same thing, except you use the C++ function lower bound. This is in the standard library function from C++, and it basically does the binary search portion for you instead of you having to write it yourself, but it is the same logic as the binary search solution. You also, this result array here, you build the array that you want, which is the longest increasing subsequence, on it, and then here you check, hey, did you find a lower bound, which means is this number lower than any of the numbers within the subsequence? Because if it is, then insert that number instead of the number that we have in the subsequence. But if it isn't, then you push back the current number, since it is probably the greatest. So does that make sense? I hope that makes sense. Anyway, goodbye.